The video explores the vital role of engineering in creating accessible and inclusive environments for everyone. This insightful look at how design principles can be applied to make public spaces, products, and technologies usable by individuals with diverse abilities is sure to inspire innovative solutions. Tired of seeing inaccessible spaces and products? Imagine a world where everyone feels included. This video explores the powerful role of engineering in creating truly accessible environments. Did you know that over 1 billion people globally experience disability? This video dives into the fascinating field of accessibility engineering, showcasing how design can create inclusive spaces for all. We've all encountered inaccessible spaces that make us feel excluded. This video explores the innovative ways engineers are tackling these challenges and building a more inclusive future for everyone. Design is a crucial and integral part of engineering, enabling the creation of functional, efficient, and safe solutions across various industries. It's not just about aesthetics. Design is the process of problem-solving, innovation, and optimization, driving technological advancements and improving quality of life. Through design, engineers can optimize existing systems or processes, making them more efficient and cost-effective. This can involve minimizing waste, optimizing performance, and enhancing overall productivity. Engineering, at its core, is about solving problems. The design process provides a structured approach to identify, define, and ultimately solve complex issues. This process also fuels innovation, encouraging engineers to think creatively and develop new solutions. Design principles can help reduce costs by considering factors like materials, manufacturing processes, and maintenance. Engineering design is crucial for producing new machines as it provides a structured approach to developing functional, reliable, and efficient machines. It involves a systematic process of defining needs, generating ideas, analyzing designs, and creating prototypes, ensuring that the final product meets specific requirements and performs as intended. Engineering for accessibility in public spaces involves designing environments that are usable and inclusive for everyone, regardless of their abilities. This includes physical accessibility, ramps, elevators, accessible restrooms, sensory accessibility, braille signage, audio descriptions, and flexible design, furniture arrangements that accommodate wheelchairs. By incorporating these principles and technologies, engineers can create public spaces that are inclusive and accessible to everyone, fostering a more equitable and vibrant community. Engineers play a crucial role in building and maintaining the networks and connections that underpin modern communication and technology. They design, implement, and manage the infrastructure that allows devices, systems, and people to connect and exchange information. Their work ensures reliable, secure, and efficient communication across various networks, from local area networks, LANs, to global wide area networks, WANs, and even cloud-based systems. Network engineering involves the design, implementation, and management of computer networks, encompassing both the physical and logical components that enable communication and data transmission. It's a multifaceted field critical to our interconnected world, spanning from home Wi-Fi setups to large-scale data centers. Network engineers ensure reliable, secure, and efficient network operations through various tasks, including configuration, troubleshooting, and security management. Electronics engineering, a subfield of electrical engineering, focuses on the design, development, and testing of electronic circuits, devices, and systems. It involves using components like resistors, capacitors, and transistors to create systems for various applications, including consumer electronics, communication systems, and control systems. While both fields deal with electricity, electrical engineering generally focuses on the generation, transmission, and distribution of large amounts of electrical power. Electronics engineering focuses on the design and application of circuits and devices that use smaller amounts of electrical power. Electronics engineering is often considered a subfield of electrical engineering. Key engineering principles in car technology include understanding vehicle dynamics, powertrain systems, materials science, thermodynamics, and control systems. These principles underpin how vehicles move, how power is generated and transferred. This involves understanding how a vehicle moves, including acceleration, braking, handling, and stability. Engineers consider factors like weight distribution, suspension geometry, and tire behavior to optimize vehicle performance and safety. Principles of vehicle dynamics are crucial for designing safe, efficient, and enjoyable vehicles. The powertrain encompasses the engine, transmission, and drivetrain, responsible for converting energy into motion. Understanding thermodynamics is essential for optimizing engine efficiency and performance. Modern powertrains include internal combustion engines, electric motors, and hybrid systems, each with specific design considerations. Selecting the right materials is vital for vehicle weight, strength, and durability. Materials science principles guide engineers in choosing materials for the chassis, body panels, and other components. Aeronautical engineering in the aviation industry is built upon fundamental principles including aerodynamics, propulsion, structures, and materials. These principles are applied to design, manufacture, and operate aircraft safely and efficiently. Further, flight dynamics, aircraft systems, and flight control systems are crucial aspects, ensuring the aircraft's stability, functionality, and maneuverability. This involves the systems that generate thrust to propel the aircraft. Jet engines, rocket engines, and propellers are all part of this field. Aircraft structures must be lightweight yet strong enough to withstand various stresses during flight. Engineers use materials like composites to achieve this balance. The aviation industry is heavily regulated to ensure aircraft safety. Engineers play a vital role in designing and certifying aircraft to meet rigorous standards. These principles are constantly evolving, with engineers working to improve fuel efficiency, reduce emissions. Satellites rely on several core engineering principles for their design, launch, and operation. These include orbital mechanics, which dictates how satellites move around Earth, and RF engineering, which governs how they communicate with ground stations using radio waves. Structural engineering ensures the satellite can withstand the harsh conditions of space, while power systems provide the necessary energy. Furthermore, principles of cybersecurity are crucial to protect against potential threats in orbit. RF engineering is fundamental to satellite communication. It involves designing and optimizing the transmission and reception of radio signals between the satellite and ground stations. This includes understanding signal propagation, modulation techniques, and the design of antennas. Satellite systems often need to support multiple users simultaneously. Principles of multiple access, such as TDMA and CDMA, enable efficient sharing of the satellite's bandwidth. The four forces simply explained airplanes fly due to a combination of aerodynamic principles, primarily involving lift, thrust, drag, and weight, and the interplay of forces like Bernoulli's principle and Newton's third law. Lift, the upward force that counteracts gravity, is generated by the shape of the wings, airfoils, and their interaction with airflow. Thrust, the forward force, is generated by the engines. Drag, the force resisting motion, is influenced by the aircraft's shape and speed. Aircraft engines, whether jet engines or propellers, provide the forward thrust that overcomes drag and propels the plane forward. Jet engines expel hot, high-speed exhaust gases, which push the engine and the plane forward, applying Newton's third law in reverse. Effective resource management in engineering involves applying various engineering principles to optimize the allocation and utilization of resources like personnel, materials, and equipment. Key principles include meticulous planning, efficient scheduling, proactive risk management, and fostering strong communication and collaboration within teams.